Okay, Matt Roscoe at the University of Montana, section 2.2, the derivative function. So we'll take in this section the idea of the derivative at a point as being the slope of a function at a point and extend it to try to determine a function that tells us the slope of the function at any point, or what's the shape of the derivative function. So in this video, what I want to do is just basically take you through the process of how do we sketch a derivative function, and then take you to some technology that can help you visualize this for a given function, and then talk a little bit about how we can use the derivative function to get a sense of what the graph of the function is doing, and vice versa. Okay, so a derivative function f prime of x. Now notice this is different than f prime of a. In our last section, we talked about the derivative at a point, with a being a specific value of x. Now we're talking about any value of x. So the derivative of the function f prime of x for any value of x can be interpreted geometrically as the function that provides the slope of the graph of f of x at the point x comma f of x. So we're going to do this by taking a look at a function itself and trying to determine what its derivative function looks like. So here's a graph of a function, and let's use this graph of this particular function to try to develop a rough sketch of its derivative function. Okay, so I'm going to step out here of the slides and go to a worksheet that I've provided you in the on our Moodle page. So please go ahead and try to find that on the Moodle page so that you can follow along with me. You might even try to do it on your own right now and see if you come back to the same results. So let's go ahead and take a look at this particular function. So we're going to use the graph of f of x to sketch a rough graph of f prime of x. So how would we do that? Well, we know that that the derivative of the function, or f prime of a, is the value of the slope of the function at a. So let's just pick different values for a and find the values for their slope. So if I pick a to be -10, then the function's value at -10 looks like it's around 7. But the question that I want to find is, well, what's the slope of that line right there that's going through the point on the function? That's the derivative, right? The derivative of the function at that point, x equals -10. So if I do that, I need to measure the slope of that line, and there's several ways we can do that. But I think the way that I'll do it, at least here for this particular slope, is I'll go over 1 and down 1, 2, 2 3/4. So I went over 1 and down 2 3/4. So that's a rise of -2 3/4, a run of 1. So it's about -2.75 or 2 3/4. So the value of the derivative, which I'll record down here below, -1, 2, 2.75, somewhere in that neighborhood, is the value of the derivative at that point on the function. Okay, let's go to the next integer value. Let's go to -9. There's the point on the graph for -9. And the slope looks also negative. So I'll start right here, and I'll go over 1. And then I'll go down, let's see, so it's going to be 1, it looks like I'm going down roughly 2, So over 1, down 2, so that would be a slope of -2 at that point. So the derivative of the function is about -2 there. I'll come over here to this one now at -8 and find its slope. A little less negative, it looks like. So let's see, I'll go over 1 and down 1 and change. So somewhere in the neighborhood of -1.25 is the slope, maybe. Somewhere in there, maybe. Pick this next point, find its slope. So I'll go over 1 and down, looks like about 1/2. I'll pick this one. Very close to 0, I would say. Over 1 and down maybe 1/4. Somewhere in the neighborhood of right there. And now I've come around to where my slope is now valued in a positive sense. And so maybe I should put it down here so you can see what I'm doing. So now the question is well, how much am I going up by? So You know, I actually am going to do it right here. So if I put it on top, I can kind of see it a little bit easier for me anyway. Over 1 and up, it looks like about a half. Over 1 and up a half. So somewhere in the neighborhood of there. I don't know, let's put this one in, see what we get. See, over 1 and up. That one actually looks more like a half. Over 1, up a half. Did I make an error here? Oh yeah. Over 1 and up a quarter-ish. It's a lot smaller than a half. So you're watching it live. So this next one I thought was closer to a half. Let's see what this one is. Now we're at -3, finding the slope at that point. See, over 1 and up almost 1, so somewhere in that neighborhood right there. Okay, let's put this one right here. That looks almost true to be 1, over 1 and up 1, it appears, so somewhere right around 1. Let's see, I'll go to this point now next. So over 1 and up a little bit less than 1. Okay, I'll go to this point now next. Over 1 and up even a little bit less than the last one, maybe 3/4-ish. I'll go to this point now. Over 1 and up looks like 2/3-ish. I'll go to this point next. Over 1 and up now it looks like about a half. Go to this point next. See, over 1 and up about a third, so I'm somewhere in there. And that appears to be almost 0, maybe just slightly negative, but somewhere in the neighborhood of 0 or just underneath it. Go to that point, and let's see. I go over 1 and down, over 1 and down maybe a half. I'll go to this point, over 1 and down 1 1/2. So I'm somewhere in that neighborhood. I'll go to this point, over 1 and down, oh, I don't know, 1 3/4. 1 3/4, somewhere in there maybe. I'll go to this point, and here I'm over 1 and down 1, 2, oh, I don't know, 2 and just a little bit more. I'll go to this point, somewhere in that neighborhood, over 1 and down 1, 2, 3-ish. So somewhere in there. I'll go to this point, really steeply negative. Let's see, over 1 and down 1, 2, 3, 3.5 maybe. Somewhere in there, 3.5 or more. So it appears that we're getting some sort of a derivative function that looks like this. Now again, we measured this, so we're not quite exactly sure what's going on, but it appears that the derivative function, if I used a highlighter here, would be something that would look, you know, sort of like this. So that's our derivative function. So f prime of x is in pink. So that's the idea of sketching a derivative, that at every single point on the function f of x, so once again the black function is our f of x, right? And the pink function is our f prime of x. Where the black function is just the function itself, and the pink function tells us the rate of change of the function at any one point. So the rate of change of the function at any value of x. Okay, so that's the idea in sketching graphs of functions, finding a derivative function. Let's see, so let's go back. So you imagine that this is probably an important thing for you to do by hand, and you have several homework problems where you're asked to do this, but it's also something that technology can really do wonders for us in terms of developing intuition. So I'm going to skip over now to take a look at how Desmos can help us do this. So I have a link here to a file I've made, and this is available in the slides. And what you see here is you see a function in red with a point on the function also in red. And so you can control that point by just controlling this slider, and you can see the point follows the function everywhere. Now the way I've made this is that you can highlight and bring into view some other things that have to do with the function. Now the first one that you can bring into view is this idea of a point on the function that's showing us the tangent line to the function at any point on the function. From -3 to 3 anyways. That's what my slider's defined for. So you can see this point sort of rolls along the function, and the black dotted line is the tangent line to the function, which we know is the slope of that tangent line is the derivative, that is the rate of change of the function instantaneously at that point. So if you add then the slope of the tangent line to the function, below that there's this point a comma g of a. So that is the value of the slope of the tangent line. So right now that tangent line looks like its slope is somewhere just under 6. I would assume that as I move it forward, that slope is going to get lower because the slope of the line is decreasing. So now we've got a slope somewhere in the neighborhood of 2. I should probably make this guy black so that we can really identify it as the slope of the tangent function. I don't know why I didn't do that. So it's associated with the black line. And then right up here someplace we go from a positive value of slope to a negative value of slope, so that black point goes from above the line to below the x-axis because of course its value changes from positive to negative, and then sort of maxes out down here in a negative sense. It gets to its smallest negative value and then starts to climb again, and we can see that in between here and here we go from a negatively valued slope to a positively valued slope, and on up it goes. So there it goes. So you can think of that black point as being the value of the black line, and the last thing that I'll show you is this the path of that black point is that particular dotted black line. So now you can see that the function in red and its derivative in black with a point that relates a place on the function to a place on its derivative function, and the black line, which is the tangent line to the function itself. So really a fun tool for you to explore the derivatives of functions, and we'll be using this tool quite a bit in our class. I do want you to be aware that you can change this function in any way you want up here. So if, for example, you wanted to put x to the third plus 2x instead, you would get this picture, quite similar. I don't see anything really different there. But what if we just had minus 2? Well, there's something very different, looks like. So now the function, drag, and we can see that its derivative function is, well, seems to be somewhat the same in its shape, just in a different position. So this is a really neat tool because it can help you generate all kinds of intuition about what a derivative should look like if you know the function. So here we have x to the fourth minus 2 in red, and the derivative of the function in black again. So some interesting graphs to explore, and I'd invite you to just use this as much as you can to develop your intuition about functions and their derivatives. And I will sort of leave it where we were, right there at the beginning, and then go back to our slides. So there are some graphical interpretations you should be aware of, and that hopefully you noticed when we were constructing these, and that is that, if we have a differentiable function f, that means it has some slope at every point, and we haven't really gotten into that much at this point, but there are certain functions where there aren't points where there's a smooth slope. So some functions are not differentiable, but let's assume we have a differentiable function and that f prime of x is its derivative function. Then what we should notice is that if f prime of x is greater than 0, that is the derivative function is valued greater than 0 on an interval, well then f of x should be positively sloped on that interval. So if it's positively sloped, it's got to be increasing on that interval. Likewise, if f prime of x is less than 0 on an interval, then the slope function is negatively valued on an interval. So if the slope is negative, then the function must be decreasing on that interval. And lastly, if we have a slope function equal to 0 on an interval, then f of x is constant on that interval, or at that point. So let's go ahead and take a look at our derivative function again and see what we can see in terms of that interpretation here. So there's our derivative function, and here is actually the machine-generated derivative function. And what do I want you to notice? Well, what I want you to notice is that the graph of the derivative function is positive in this interval, and it's negative out here and negative out here. So let's draw in some regions here. I'll just draw some rough lines across this graph. So there, and at the point roughly x equals 4, somewhere in that neighborhood, we have this sort of these two different pieces of the graph that we can kind of think of. So in purple, let's see if purple will work. Well, purple now, let's do green. This purple's too close to pink. So green in here, and we'll do green out here as well. And what does that mean for the function? I'll do the function in green as well, and I'll do the function in green as well here. Okay, very nice. What should I do, orange or purple? Let's do orange, why not? I'll do orange in the middle here and orange in the middle here. So what do I want you to notice? Well, here's what I want you to notice. I want you to notice that that in this region, f prime of x and f of x so in this region, f prime of x is negative, so it's, I'll put a minus for negative. In this region, f prime of x is positive, and in this region, f prime of x is negative. So we have negative, positive, negative. So what does that mean? Well, that means that if the slope function, the derivative of the function, is always negative in this region, then the function itself must be decreasing. So in other words, its slopes must all be negative, so it's got to be decreasing. Okay? In this region, since the interval, across this interval, the derivative function is positive, that means that everywhere on that interval, the slopes of the function must be positive, so it must be increasing. So that's an increasing part. And then here, again, we dip negative in the derivative function, so that means that all the slopes of the function at every point in that region must be negative, and so it must be, again, decreasing. Okay, so that's the generalization I was hoping you would have noticed. And one thing also to point out is that, that there is a spot in between negative and positive where the value of the derivative must be equal to 0. It's somewhere right in there, and it's somewhere right in there. And when it is equal to 0, then what we have at that point is just an instantaneous slope of 0. It only occurs for a single point, at least in this case it looks like. And then we switch. So along these dotted lines, there's actually a spot too where this actual derivative should be valued at 0. And that'll be important later in the course for identifying what we call local maximums and minimums of functions. Okay, well that pretty much concludes what I wanted to show you from this chapter. And let me know if you have any questions, and good luck on your homework and quiz.